Welcome to this lecture on field programmable gate arrays in the course Digital System Design with PLDs and FPGAs. In the last lecture we have looked at the Virtex, Xilinx Virtex configurable logic blocks. We have looked at the lookup tables, how that can be combined. Then we have looked at the flip flops and we started with the carry chain or the carry logic. So we will continue with that. We will continue looking at the carry logic, the flip flops and something with the clocking and all that in today's lecture. And so let us briefly look at the last lecture's portion so that we get some continuity. See, this is the CLB or the configurable logic block of the Virtex FPGA. It has two identical parts called slices, and within a slice you have two identical parts. One part consists of 4 input lookup table which can implement any function of any boolean logic function of the 4 variables. The output can go to a flip flop, and the detailed diagram we have seen here, and we said that this is the 4 input, this is the output that can be used as a combinational output. In that case this flip flop can be used separately with this input. If you want, you can register the output, which is a case of a data path or a sequential circuit and so on. You could combine the 4 input lookup table using this mux, and the select line act as a 5th variable, and such 5 input 2 lookup table can be combined with this, because assume there is one here 2 lookup tables which is formed a 5 input lookup table. The output of that F5 mux come here, and F6 mux can make the 6 input lookup table, and this is the 6th input, and this can be taken directly out or through a flip flop. In that case like if you don't use the flip flop, if you don't register the output using a flip flop, this flip flop cannot be used because this is used for the 6 input lookup table. Same is the case with the 5 input lookup table and this flip flop. And we have seen that this the flip flop has a data input, the Q output, set and reset, okay. And the clock can be connected to, there are options to connect it to the different clocks or the user clocks, okay. There are global clocks and the user clock, and we will come to this after like we will what is the CC we will talk about as we go along. So I have shown all that using the lookup table and flip flop separately together, forming the 5 input lookup table from 2 4 input lookup table, and forming the 6 input lookup table with 2 5 input lookup table, so which consumes all the 4 input lookup tables, okay. And we have also seen that it is not necessary that you have a 6 input function. Always you need to use the 4 lookup table, okay, 4 input lookup table. Depending on what function you are implementing, you could cascade lookup table and implement that. We have seen an example of 6 input ABCDE and ABCDF. So there is a common product term, and we take it out and implement that in a lookup table. That output is cascaded. That output is X is cascaded with E and F to form the real output, the Y, okay. So it is not that whenever you have 6 input you need to go for a 6 input lookup table, okay. You could cascade 4 input lookup table. This shows a 5 input function using 2 cascaded lookup table than and F5 mux and combining them. But there are cases you take this function Y is ABCD XOR E, you are forced to use the tool definitely has to use the 2 lookup table with the F5 mux, there is no other way. So this is a summary, and we also said that the lookup table is nothing but a memory, 1-bit memory, and when it is 4 input lookup table it is 16 into 1 RAM, and the RAM write usually is controlled by the configuration circuit, because the lookup table is written during the FPGA configuration. So the case is that if by chance there are a lot of lookup tables not being used in your design, this memory goes waste. Okay. So the write control is also available to the general purpose routing line. So in principle you could use this lookup table as a RAM, and you have to use the tool core generator to instantiate it. The only thing is that then it cannot be used for logic. But if you have a design wherein lot of lookup tables are remaining free, and you have used up all the block memories, the hardcore memories, then you could use this as a memory. And since the lookup tables are distributed all over, it's called distributed RAM. And I mentioned that there could be kind of variable latency because it can be distributed. One need to take care, because if the output is not registered, then there you would experience in the read different delays that could kind of mess up your design. Suppose example is that suppose you are trying to generate a waveform by lookup table. Okay. Then you will find that in a waveform generation you will store the sample and output it at the regular intervals, and if the read access of the memory is variable, then there will be jitter and the distortion will be in the waveform. Okay. So you might not think about it, but this could be the result. Okay. So if you use the distributed RAM for waveform generation, huge waveform with lot of samples stored, then you will find that the waveform is kind of distorted depending on the frequency of the waveform. Okay. So if it is a very low frequency wave you are trying to generate, may not create much problem, but if you try to read the memory very fast, wherein this variation in the latency affects it, then you have a problem. So you should take care of that. Okay. So let us come to the carry logic. So this is the full adder. We are talking about a ripple adder. So this is a ripple adder equation. The sum of ith stage is AI exclusive over BI exclusive over CI, and the carry of that stage output carry is carry I plus 1, because this is the carry input to the next stage SI plus 1. Okay. And that is AI BI or AI exclusive over BI and CI. That means that the carry is generated if both inputs are 1 1 1, then you definitely know that the carry is generated. It does not matter the input carry is 1 or 0, because 1 plus 1 is 0 and the carry goes out, and even if this carry input carry is 1, it just kind of it just it becomes 1. So the sum becomes 1, it does not matter. And if not, if both are not 1, if either of them is 1, then the carry out will depend on the carry input. If the carry input is 1, the carry output is 1. So that is what the equation say. Now if you implement this in FPGA using lookup table, you would need one lookup table for SI, one lookup table for CI plus 1, because lookup table has only one output. So for a 4-bit adder you need 8 lookup table, much more than that. You know that the CI plus 1 should be kind of using the wires, should be connected to the input of the next stage. Okay. So a lot of wiring is required, and this will slow down the adder. Okay. Now if adder is slow, the multiplier will be slow, and so on. All the arithmetic operation will slow down if the adder is slow. So this happens because there is interconnection between the adder stages. So one thing we can do is that the carry equation can be implemented in hardware, we will see how it is implemented. Okay. That then can propagate like CI, there is a dedicated hardware along with this SI stage, and the CI plus 1 go to the next stage without, not through the programmable interconnection matrix or the programmable switches, it directly goes by the wire. So that is how it is speeded up. So I think we have just started describing it in the last class. So this equation is implemented here, in this lookup table, and this mux, okay, that is what it does. So we will see that in the real CLB, but before going there, so this is the lookup table, a 4 input lookup table. What is done for AI BI is that AI and BI is connected here. Mind you, the CI is not connected here. It is not that you implement the sum by AI exclusive or BI exclusive or CI in a lookup table. It is not done, because you see the trick is that you see AI exclusive or BI is common to the sum and the carry. Okay. So the idea is to implement this common thing in a lookup table. So that is one done here. So you connect AI BI, implement the XOR of AI BI, and now this mux will form the carry, this XOR will form the sum. Okay. So these are kind of dedicated circuit. So this will form the AI exclusive of BI, and you can see that it is coming here combining with the CI from which is coming out of the previous stage. So this XOR form AI exclusive of BI exclusive of CI, and the sum comes there. Okay. And that can go out directly or can go to a flip flop. Now you see this, the AI exclusive of BI is a select line of this mux. Okay. So if it is 1, assume it is 1, then you see the CI, so that this is the path. So CI plus 1 equal to CI, that is what is this equation saying. So if this is 1, then the CI plus 1 is CI. Okay. So if either of the bit is 1, the carry depends on the input carry. So if the carry input is 0, then the carry output is 0. If carry input is 1, carry output is 0. If it is not, like if this is 0, then the carry I plus 1 is AI BI. So you can see that if it is 0, this path is selected. Now there are two possibilities. If this is not either of them is not 1, then there are only two possibilities, both can be 0 or both can be 1. Okay. So it is enough that you do not have to do an AND, you just pick up AI and connect it here. If AI is 0, then the carry output is 0, AI is 1, then both are 1, because 0 1 1 0, this is the path selected, 0 0 and 1 1, this is the path selected. So if both are 1, then AI definitely will be 1, that is enough, and the CI plus 1 go to the second stage exactly like that. Okay. So let us go to the CLB, the slice diagram, and you can see that, say look at here is where AI and BI are connected. You form the AI exclusive of BI in this lookup table, and you see that is coming here to this exclusive OR gate, and the carry in from the previous stage is coming here through this mux and is combined with the AI exclusive of BI, and you get the sum. So now you can take it out directly, or you can register it through a flip flop depending on the function you are trying to implement. If maybe you are trying to implement a counter, then it goes here. If you are not registering it for whatever reason, then it goes out directly. Okay. Now you can see the other function AI exclusive or BI is going to the select line of the CY mux, and you see that the CI plus 1 is nothing but CI then if it is 1. If it is 0, you see the AI or BI is coming as an input. Okay. So this is the carry logic which is implemented. it works definitely along with the A exclusive of BI here, and it goes there and it forms the carry logic for the next I+1 index, and this is the sum. So the sum is formed using this lookup table and the XOR gate. In the I+1 this lookup table and the XOR gate, and the carry circuit is here for the ith stage, I+1 stage is this, and so on. It goes like that, and you can see there is a mux, input mux in this stage. This allows, you can see that if you are starting the 0th stage of the adder is this stage, then you can have a carry input to the stage, okay. Like the first stage can have a C0 or C in 0. So that is what is this for, which is not available here. It will be available only in the next slice. So that is how it goes. I hope that is clear to you. So the suggestion is that when you implement an adder in FPGA, you don't write the equation of the adder using a loop or a generate as we have shown in the VHDL, because when we discuss VHDL we weren't discussing probably the FPGA implementation part, we were discussing the VHDL synthesis, okay. Now when you come to FPGA, if you write equation for a ripple adder, then it will get implemented, everything will get implemented in lookup table and everything will be slow. So to be able to use carry chain there is one direct method, there is very circuitous method. The direct method is that use the operator plus, okay. So you want to add A and B, you just say C gets A and B, okay. It's straightforward. Otherwise you can go very low level, you can start playing with the lookup table, carry logic, instantiate them, interconnect them and all that, but not a very good idea, not required. So advice for the FPGA design is that whenever you try to use a plus operator, it will use the carry logic. When you use a counter and higher level function, somewhere this plus will appear. You say count gets count plus 1, you know, we have seen that in our example. Then automatically the carry logic will be used, and there is an AND gate which is shown earlier, which is used for the partial product implementation in the case of a multiplier, and in some cases the carry chain can be used as for cascading. That means that you implement say suppose the inputs are 4 ABCD, then you implement A and B and C and D. Suppose you want to AND it with say EFGH, there is a way that you know it comes here and in this kind of circuit, and that gets ANDed here and you can take the output, okay. So not all the FPGAs, at least not in the Virtex, but then there are FPGAs where this AND cascading or cascading can be done, and you can think about it. It's very easy with a multiplexer kind of scheme, it is very easy, okay. So that is this, then in that case it is called cascade logic or cascade chain. So let us come to the flip flop now, this part. I want to talk about this EC, or it's called enable clock, and when we discuss our initial case study of the CPU, we said the controller will control the data path. Many times it will control enable a register or a counter or things like that. In such cases, and we have seen one foolproof way of implementing that is using a recirculating 2-to-1 mux, that suppose this is a latch signal from the controller and this is the register, then what happens is that when the latch is 1, the input gets registered. If the latch is 0, that output gets recirculated, and there is no timing issue. If you do clock gating, there was a timing issue. Since the latch signal is coming from the state machine, there will be a delay with respect to the clock, the TCQ plus TCOM delay, and you can see that this enable signal will come offset to the clock period, and in the next clock edge when the clock comes here to the register, in this edge the data is coming in from here, it gets latched, and the data has lot of setup time, you have all the time to set it up, okay, because it gets enabled much before the latching clock edge, okay. So that is what is this recirculating mux does. Now this recirculating mux is built into the flip flop of the FPGA. So the real FPGA flip flop is a kind of what to say, it's 2-to-1 mux plus the flip flop combined, okay. So this gets into the to the flip flop, and this is written as clock enabled. So whenever you see that, you assume there is a 2-to-1 mux with this clock enable as a select line, which allows you to kind of implement an enable signal. So you look at this VHDL code which say that if clock tick even and clock is equal to 1, then if some control signal is 1, then Q gets D, okay. So normally some 2-to-1 mux is required to implement that, but in FPGA, since it is built in, whatever is a control signal is connected here, the clock is connected here, and this is the D, this is the Q. You don't have to do anything, okay. One level of 2-to-1 mux is available, but then you need further control, then you need to have the muxes outside. This wouldn't help you, but in most cases on an average you need kind of one level of control, enabling a counter or enabling a register and so on. So that is easily implemented using this clock enable, and some vendors call it enable clock, okay. So some people call it CE clock enable, some people call it EC enable clock, kind of to make a difference probably between the devices, okay, or vendors. So now let us see how the circuit get mapped to this scheme of this kind of architecture. So one thing is that suppose you have combination circuit, you know that lookup table is used to implement. It can get combined if there are more inputs like 2 4 input to 5 input, 2 5 input to 6 input and so on, okay, and can be further combined or it can be cascaded, okay. So basically when you have a kind of combination circuit, it will be implemented in one or more lookup table. It could be cascaded, it could be combined using muxes, whatever it is. But if you have a data path, okay, I have written sequential circuit, but then assume it's a data path or a part of a sequential circuit, doesn't matter. You have a flip flop through a combination circuit, the flip flop, okay. So there are in the slice or the CLB, there are a lot of flip flops. All these get implemented in the flip flop of the CLB, and the flip flop output goes to the combination circuit, the combination circuit goes to the flip flop, and this get implemented in one or more lookup table. And we have seen in the diagram the combination circuit output can be taken to the flip flop, okay, and this can come from the flip flop before, okay. So that is how it gets implemented. And if you take a FSM finite state machine, you have a logic, output goes to flip flop output is fed back to the logic and some input comes there. So again same thing, you can implement the next state logic using lookup table, which gets the fed back flip flop through some wires, and the input is coming with the wire, and the output of next state logic is going to the flip flop, and the flip flop output again goes to the output logic. So that if you look here, you have the lookup table which is acting as next state logic, the output goes to flip flop, this output is fed back here to form the feedback, and this can go to the next stage lookup table to implement the output logic. So that is how things get implemented in FPGA. And let us look at the IO block. Okay. So we have seen that all around the FPGA are IO pin, attached to IO pin is an IO block. Okay. So the star of IO block, or the main element which implement this IO functionality, is this tri-state gate. Okay. So when there is an enable, when there is enable, it acts as an output. When it is cut off, it acts as an input. So there are essentially 3 paths. One is so this is an IO pin, and you can assume the FPGA wires are here to which all these signals can be connected. So there are 3 paths. One is from these wires, internal wires, to the output pin, from the output pin to the wires inside the FPGA like this, and there is an enable signal which is also controlled by the wire. Okay. So 3 path: output, input, and the enable path. Now all this can be combinational, it can come directly, it can go directly, and this enable path also can be combinational. But see, there are 2 things. We might get an input which is not synchronous with the clock here, so it can be input synchronized. Okay. We have seen the problem of metastability. We told about the synchronizer, single state synchronizer. So you have the option of taking the input directly inside to connect to the wires, or through a synchronizing flip flop, and that flip flop has, you can have the clock selection, multiple clocks, the clock enable, the reset, all that is there in the all the flip flops. Okay. Now there is a programmable delay which you can add input delay to make the hold time 0, because to meet the hold time is quite a tough thing, and we have seen that hold time, for the hold time violation not to happen, TCQ plus TCOM min should be kind of greater than the hold time. So many a times if the hold time is large, it is difficult to meet. So this can be adjusted to make the hold time 0, but it will increase the setup time, it does not matter. Similarly you have the enable path, and that can kind of come directly through a combinational path, or it can come registered. Okay. So that's a basic IO block, and sometimes some voltage standard you need to give a reference voltage, and that is this particular pin. So these pins support various IO standards which can be programmed in the constraint editor. Okay. We will see the constraint editor when we discuss the tool, but this kind of it support various voltages, maybe 3.3, 2.5, the PCI standard, because where different things can vary, and the slew rate can be programmed, the rate of change of output can be programmed. You can program a pull up resistor or a pull down resistor. We have discussed that if it is tri-stated, this will be in high impedance and it will pick up noise, and if this is an output, whatever is connected at the output, those inputs can start switching, because it can be maybe near to the threshold voltage, then a slight noise make it go up and down to the actual logic level, and the input circuitry can switch and dissipate power. So this avoid that, you can pull up, pull down, and there is a whole circuit or a weak keeper which remembers the last value. So if you can choose either pull up, pull down, or this. Okay. This is a latch which latches the previously driven value very weakly, so that also can be a program. So essentially this is what that slide say. There are 3 paths: output, input, and tri-state. It can be taken directly as a combinational path or through flip flops, and flip flop has set, reset, clock enable, clock selection, and all that. Programmable delay can make the setup time 0, sorry, hold time 0. You have the programmable pull up, pull down, hold and slew rate, all that is programmable. Okay, you can program it. Sometime you have implemented something in a CLB, okay, and that the CLB output is taken to a pin or a pad. So what the tool does is that it will move that flip flop, okay, to the IO block, because it is very nice to have the last latching or registering at this point, because if it is somewhere inside a CLB, then again you have to take the wires, that will add lot of wire delay, and which may create timing problem with the following the circuit, following logic. Okay, so many times it's a wise idea to register the output before leave the pin, because that goes with the minimum delay. So after the clock edge there is a TCQ delay, so there will be less timing problem for the input. Okay, whichever circuit is using this output as an input will have less problem. Similarly, like we have the input which if it is asynchronous we can synchronize. Similarly, if everything is synchronized, this tri-state enable also can be synchronized, and it support various IO standards, CMOS 3.3, 2.5, 1.8 and all that, and all the time there will be kind of core supply which supply to the internal and the IO block supply, because the core can work at a low voltage resulting in low power dissipation, and when it comes to the IO pins this can be scaled up, because if the swing is more there will be more power dissipation, and so the many times the most recent chips, not only FPGA, the core will work at a low voltage near 1 volt, and when it comes to the pin it is scaled up to 2.5 or 3.3 volt. So that is done in FPGA 2, and this is the whole circuit. Suppose you have a bus, and if you program the whole circuit to the bus, then what happens is that suppose the bus is driven 1, then what happens, this 1 is latched here and 1 comes here, this becomes 0, this 0 will become 1 and it gets latched. But if you put a normal latch, then this inverter will drive that bus very strongly, and if somebody some other output is driving it to 0, and if this is driving it 1, there will be a short circuit. So that is why a high resistance is kept here, which will weakly drive the bus and hold on to the previously driven value very weakly. Very weakly means that since it is through a resistor, some other output can pull it down, okay, make it 0, and since there is a high impedance nothing happens, otherwise there will be a short circuit. So that is what the purpose of the whole circuit, which remembers the last value on the, which keeps hold on to the last value of the bus, and thus avoid the glitches and switching, unnecessary switching, which is dissipating power and create noise and so on. Okay, and this is the view of the internal wiring structure. You have lot of wires. There is a huge switch here which connects all vertical horizontal wires together, and the input to the CLB is from here, but in Virtex CLB there are connection from this switch directly to the CLB. Okay, so that is what is shown here. This is that switch which connects to the adjacent switches. So this is that switch here, and this is the logic block. So this is the logic block here. What it shows is that switch has direct connection to the CLB, okay, and the CLB output is fed back to the CLB input. So it need not go through the general wires. Okay, so it is not that the CLB output is directly taken here. Suppose it has to be taken to the input, it need not go like this, come all the way back and from here. Okay, it can directly go to the input, and it also shows that if you have adjacent CLB it is directly connected. So there is a CLB here, that there are some output going to the input of this CLB, or similarly some output from CLB is coming to the input of CLB. So there are no programmable interconnections. So it is very fast, the interface between the adjacent CLB is very fast, okay. That makes, if things are close together, the delay between them is very minimal, okay. So these are kind of some statistics of the Virtex routing wires. The adjacent CLBs are directly connected. There are 24 single length line. So it means that you take a switch like this, between the switches here there are 24 wires, okay. Between these switches there are 24 wires, between these switches there are 24 wires. And you have 72 buffered hex line, that means from one CLB to the 6 CLB. So from here to the 6 CLB there are single wire running, okay. So that makes the lowest very large lengthy connections less costly. Otherwise if it's single length wire, it needs a lot of interconnection to reach the destination, and it will all add to the delay. But this will reduce the delay from the first stage to the 6th stage, okay. And there are 12 buffered long line, that means there are lines running from one end of the chip to the other end of the chip, okay, and not only horizontally but vertically also, okay. So per channel there will be 4 tri-state line, both horizontal and vertical, and there are separate line which can form tri-state line or busing. So every CLB has 2 output through a tri-state gate which is connected to some 4 common wires in some fashion. So essentially, and the 2 output is connected to the 2 wires. So you can form a bus using this tri-state gate as the output of the CLB, that is possible. So let us now ask, having learned all the architecture, we have looked at basically the architecture of the CLB, we have understood how that is interconnected and so on. So let us just try to estimate some resource requirement. So my question is that, say we have a finite state machine, it has 2 inputs, okay, external input, it has 3 states and 2 milli output. How many CLBs you require in a Virtex FPGA to fit this finite state machine, that is a question, okay. So if you look at the finite state machine, you have an XAD logic which decode the present state and the input, okay. So we have to look at to decide how many lookup tables this will combine, this require we need to know how many flip flops are there and how many inputs are there, okay. Similarly you have to determine the number of flip flops required, and you should remember that XAD logic is required for each flip flop. If there are 4 flip flops here, then there is a Q3, Q2, Q1, Q0. So there will be D3, D2, D1, D0, and the XAD logic should give 4 output to connect to D3, D2, D1, D0, okay. So let us work out this requirement and this requirement, okay, for this case, and we know that the Virtex CLB has 4 input lookup table and a flip flop and such 4 of them, okay. So we have this was the example, we have a finite state machine with 3 state. So it requires 2 flip flop to implement in a binary encoding. So the XAD logic has 2 inputs and the present state, which is 2 cues from the current flip flop. So the XAD logic will have input 2 state variable, the present state, and 2 inputs, so that is all. So 4 input. So and you know that there are 2 states like Q1 and Q0. So we need to decode for D1 and D0. So there are 2 4 input lookup tables are required, okay, because 1 4 input lookup table is required for one bit, and so you require 2 4 input lookup tables for the next stage logic. And when it comes to output logic, we have a melee output and that decode the present state, and I have not shown but the input also. Okay. So there are 2 flip flops, 2 inputs, so there are 4 input output logic, and that occupies 4 input logic will require a 4 input lookup table. So that is shown here, that is you have output logic as 2 input because we say 2 input, and 2 state variables because there are 3 states and Q1 and Q0. So you require a 4 input lookup table for output, but we have 2 outputs, so you need 2 4 input lookup tables. So we need 2 lookup table for next state logic, 2 flip flop for state variable, and 2 lookup table for output logic. So if you look at, there are 4 input lookup table and 2 flip flops, and in a CLB we know that in a CLB we have 4 lookup table and 4 flip flops. So this require 4 lookup tables and 2 flip flops. So basically this require 1 CLB minus 2 flip flops. So you can see the kind of the power of this architecture. A small state machine require only 1 CLB to implement. Okay. Similarly, let us take an example of an 8-bit counter with parallel load feature. That means a normal 8-bit counter with a reset, and also it has a synchronous load. Okay. We have seen the circuit of this counter. So if you look at it, you have the 8-bit Q7 to Q0 flip flop, and that is incremented and given it here. There are for parallel load there has to have a kind of load signal and the data in signal. Okay. That is required. So for each flip flop if you take there will be kind of 8 things fed back, and you have the load and the data in and all that. Okay. So we come to this 8-bit counter, you need 8 flip flops. Now the incrementer can use carry chain, so essentially we need only 8 lookup tables, and this carry chain will implement the +1. Okay, because you know that you can have think of an adder with the carry input as 1, then will implement the +1, and that can go to the flip flops here. But so you have the input, suppose whatever is a Q will come here, and the carry chain will use it as an incrementer with a +1. This BX will be 1, and that will add 1 to everything. You don't need to give a +1 at the input of the lookup table, but this can be used for +1. So that is how the counter get implemented. Not only that, we need a load feature and a data input, so that you know that now the load can be given here and the data in for that corresponding variable can be given here. Still we need only a 3 input lookup table, but there is 4 input lookup table. So that is enough to implement the incrementer plus the multiplexer for multiplexing the input value. Okay. So essentially we require 8 flip flops, 8 lookup table with a carry chain. Okay. So that is what is required. You have 8 flip flops, incrementer use carry chain, next state logic will use 1 state variable for +1 and 1 load signal and 1 data input signal for loading. So 3 input per state. So NSL next state logic require a 3 input lookup table. So we need such 8 for 8 flip flops. So 8 lookup tables, 8 flip flops. So there are you will end up with 2 CLB or 4 slices. Okay. So you can, if you have a circuit, if you know what is inside a circuit, you can estimate how much resource is required to implement that circuit. Okay, knowing the logic lookup table. So as I said, we are discussing the Virtex architecture. The Virtex chip is not available now. The higher the recent version of the Virtex is there, Virtex 5, Virtex 6, Virtex 7, different versions. Now you can look at and you have the Spartan 3. Spartan 3 has a similar architecture as a Virtex, but Spartan 6 which is quite different, so all these now you can go back, look at the architecture of the CLB, and you can understand the functionality. You can, given a code, given a spec, you can estimate how much lookup table, how much flip flops are required to implement this functionality. Okay, so that is that can be easily done. So we will take one more kind of example. What I do is that I will give a VHDL code and let us see how that VHDL code gets implemented within the CLB, the logic block using slices. Okay, so this is the library and the package declaration. This is the entity declaration, very simple entity, A B C D E F G H. So you have 8 input, 1 output, it is a combination logic. The architecture, you write a process which is sensitive to A and B, begin, if A is 1 then Z is 0. So it looks like a reset, A is a reset, Z is an output, else if B tick even and B is equal to 1. So we know that B is clock, A is reset, Z is output. Underneath we say if C is 1 then Z is D and E and F and G XOR H. Okay, so we again know that when you say under this if C is 1, it is a control signal. Okay, so this can go to the clock enable because that can enable the recirculating marks, and Z is the and a 4 variable XOR the 5th variable, and we have discussed this in the last lecture. You need you cannot cascade 2 lookup table, you need to combine 2 lookup table with an F5 mux to implement this, because this is a bar and this, or this as it is and H bar. Okay, so that is how the equation comes. Then you need 5 input lookup table. So that is the essence of the circuit. I have not shown the synthesized circuit because it is easy to imagine. A is the reset, B is the clock, C is the enable clock, Z is the output. This gets implemented in a 5 input lookup table. So let us come to the slice diagram. So we need to combine 2 4 input lookup table using the F5 mux. Okay, so D and E and F and G are common. So you see D, E, F, G is connected through the wire to the top lookup table. Same D, E, F, G is connected to the second lookup table, and that is, you can see the output is going to F5 mux. The select line is a 5th variable which is H. So our logic gets implemented here. Okay, so that is what is the logic here, that goes to the D of the flip flop. Now we have to implement the C, that is nothing but, so this F5 output has to go to the flip flop here. So you can see that this take through this mux, it comes to the flip flop, and you see the enable clock is connected to the C because that is a control signal as the code suggests. Now B is the clock, and you can see the clock is this pin and that goes to the B. Okay, so assume that there are wires before the lookup table in the channel, and these are connected to the wires there using some switch there. Okay, now we have one more point, A is the reset. So you can see that A is a set reset, A is connected here, and that blue line goes to the init of the flip flop. So that is get reset. So you can even so the idea here is that there is no magic, and most people don't look at the CLBs. Okay, so however complicated the CLB is, that is nothing much, it is lookup table. Now you go to a higher FPGA, you might have a more complex lookup table, like instead of 4 input lookup table they will have 6 input lookup table, and sometime within that lookup table itself is composed of 2 5 input lookup tables. So here what we have is 2 4 input lookup table which can be combined into 5 input and 6 input, but in a complex FPGA you might have a multiple 6 input lookup table which can be used as 2 5 input lookup tables. So like that, they play with this kind of functionality, but if you spend some time you will be able to understand this thing, and given a code you can even kind of draw the synthesized circuit, and you can kind of place and route manually, I mean for your understanding to the slice or within the CLB. And what you can do is that you can write such a VHDL code using the tool, you can implement it, you can place and route, and there is a floor planning tool, you can go inside and you can literally see that connection, you can trace these wires inside. Maybe when we discuss the tool, when I show the demo of the tool, which I keep it to the end, because the problem with the tool is that the tool gets modified, changed, all the GUI change, the menu change, the more functionality is added, and if I start introducing show things in the middle of the lecture, middle of this course, and after say 1 or 2 years if this course survive, it's found useful, and then this will become, that part become outdated. So I am keeping that towards the end. I hope you will have the maturity to kind of quickly adapt to that kind of thing, that every lecture we don't need to show a tool and make it work and things like that. I keep that towards the end. So that is how, so let us come back to the slide. So that is how given a VHDL code how it is mapped here. Definitely I skip one step, I didn't draw a diagram, the schematic of the block schematic which the synthesis tool synthesize. You can do that because it's fairly simple, that's why I didn't draw. So that's how things happen, and the Virtex has the block memory built in. Okay, the Virtex FPGA has dedicated memory built in, which you, if you want to use, you should not write the VHDL code for it. What you can do is that, though the tool allows it, you can instantiate the template for this using a tool called core generator. And if you see, this dual port memory is quite useful because it's unlike the normal memory with a single port, it has 2 ports. Okay, so you can see that there is 2 address line, 2 data line, and 2 write lines, 2 enable lines, and all that. So this is a single memory, and of course the data input and data output is separate, which is true of every memory chip, because you can imagine the memory cell inside, or you want to assume the flip flops inside in each location, and the data input is the D of the flip flop, data output is the Q of the flip flop. Okay, only thing is that there will be multiple location depending on the location you want to read, there will be a mux there. The address goes as a select line of the mux, and appropriate location is mux to the output. Okay, and similarly the input goes parallelly to all the flip flops, but this address line will clock the correct location. Okay, so there is an address decoder which enable the clock to the input of the flip flop. Okay, so in principle you can have the multiple port, you have the same location, use another mux with the second set of address line to read another location. Similarly, as you are writing to one location, you can have an address decoder clocking yet another location. So that is how the dual port RAMs are built. I have not shown the internal details, but you can imagine it's not a very difficult thing to imagine, and in principle you can build any number of ports, like you can have a 3 port, 4 ports, it does not matter, but at least what is useful is a dual port, because many a times you can write using one port and you can read using another port. Okay, So that's very useful because maybe somebody some hardware which is computing is writing to the memory location. At the same time the earlier output can be read and computed, okay. So you can see that the computation can go uninterrupted. If it's a single port memory this computation block has to write then stop it, then the read computation the computation here has to read using the same port and read it, okay. So there is a the throughput will suffer, the dual port will allow you to kind of write and read at the same time different location. If it's same location of course there will be a conflict if one port is writing and one port is reading the same location, okay. Then there is a problem, what is maybe read may not be correct, okay. And you should also know that there is no great thing about input and output data line. In a normal chip it is multiplexed together to save the pin, but in a it is very ideal to have separate input and separate output because you don't need a mux select, like you don't need separate write read select and all that, which avoids that. So that is how the dual port is implemented. So it's true dual port, each port can be read or write or read or only read or only write. It's all synchronous, it works with the clock edge, when a clock comes this gets latched, the address is used, data is used. Similarly when a clock comes the read happens, okay. It can be instantiated through core generator tool, the various blocks can be combined for larger width and depth, and if the same location is accessed there is conflict and the read can be wrong, and the memory can be initialized in VHDL code, okay. Like you can instantiate it and you can write some pattern to start with in the memory, and so while configuring the FPGA it gets written, so that can be specified in the VHDL. So I think we have come to the end of the lecture. What we have seen today is basically the carry chain, how it implements the fast adders. Then we have looked at how the sequential circuit, the FSM gets mapped into the basically to the CLB. We have seen the IO block, we have seen the whole circuit, we have seen the little bit the tri bus line, and we have seen some example of fitting an FSM counter, and given a VHDL code how to even trace the routing within a CLB, and we have seen the block memory usage, okay. So we will wind up here, we will look go ahead with the configuration of the FPGA in the next lecture. So I wish you all the best and thank you.